Hello everybody. In this video let's get into the time constant of RC circuits, its calculation and how the RC circuit responds to a continuous AC source. Here is a circuit with a 10-volt battery, a switch and an RC circuit. When the switch closes, the capacitor is slowly charging with a time constant until the capacitor voltage reaches the voltage of the source. Here is the entire charging process recorded over a time span of 10 seconds. The time constant of the circuit is evaluated by drawing the tangent to the charging function. In this case, the tangent touches the curves at the instant when the switch closes. The time constant is equal to the time span between the closing instant and the crossing of the battery voltage, e.g. 10 volts. The time constant is equal to R times C, and with given elements of R equal to 2 kilo ohms and C equal to 1 millifarad, the time constant can be calculated. The result is the same as before with the graphical evaluation, namely 2 seconds. Now the previously charged capacitor is discharged over the same resistor. To do so, the 10-volt battery is replaced by a short circuit and the capacitor initial voltage is set to 10 volts. The resulting time constant is 2 seconds as before. The time constant is independent of the charging voltage. It solely depends on the values of R and C. The graphical evaluation of the time constant does not have to start at zero. The tangent can be set to any point of the curve. The result will always be the same. By the way, the charging current has the same time constant, of course, but with inverse sign, as demonstrated by the green current curve. For an experiment purpose, the DC battery is replaced by an alternative voltage source, for example with a frequency of 1 Hz. First, let's check the frequency domain. At the frequency of 1 Hz, you see that the voltage amplitude at the capacitor is 0.79 volts, provided the source voltage continues to be 10 volts. Back to the time domain, the voltage at the capacitor shows 0.793 volt as well, as expected. Efficient learning comes from doing. Play around with the elements by means of sliders in both the time and the frequency domain. Both is possible on the simulator ecsb.ch. In order to close the loop, here are the math formula for the alternative current sourcing. If you want to quickly and easily build an electric circuit model and interactively play with the elements, this is the place to go. For example, you can change the phase angles of the power sources in real time and watch the resulting changes in the power flow across the grid. There is no better tool to get hands-on expertise in electric circuits. You can access the browser-based tool via link below, www.ecsb.ch.